In this class, we're going to look at some examples on source-free RC, RL circuits and how to work them out. So I have a few lined up examples coming from past test and past exam papers, and you'll see exactly how to approach them. Now, the first thing that you have to see is how do you differentiate or how do you identify a source-free circuit so that you understand how to approach it. Because there will be two types of circuit. In a source-free circuit, at t is greater than 0, you're only going to have an expression that gives you the natural response. And for a circuit which is not source-free, you're going to have the component of a forced response. Now, how do you differentiate a source-free from a circuit which does not resort to source-free? Look at this circuit, for example. At t is equals to 0, what happens? Notice that here, this is simulating that the switch is being opened. So if the switch is being opened there, notice that only this part of the circuit will remain. And in this case, that part of the circuit that remains, notice that it does not have a source anymore. The source would have been cut out from the circuit. This is why at t is equals to 0, as the switch is opened, the circuit remains source-free. Let's look at this example as well. In this case, they're saying that, so again, pay attention to the action of the switch there. Initially, the circuit is like this. So this is what we have initially. The switch is initially connected to point A. So this is what was happening. And then what do they say? The switch is moved to position B at t is equals to 0. So at t is equals to 0, once we start observing time, the switch is moved to position B. What does this imply? It means that now it is disconnected from position A, and now it connects only to position B at t is equals to 0. This becomes our circuit. Just this part in red. And notice that if you pay attention to the part in red, observe that the source has been cut out. So this piece in red becomes a source-free circuit. Even as they continue to say that at t is equals to 1, the switch is moves from B to C. Even after that, at t is equals to 1, it moves from B to C. The switch is now here, meaning this is our circuit. Notice that even in this case, our circuit is still source-free because this part in red does not contain a source. Now, a common problem that students tend to confuse this with is the expression that has a forced response. Look at these in details later when we describe how the forced response comes about. But look at what happens here. Here they're saying initially the socket, the switch is connected to this point. But at t is equals to 0, the switch opens up. So this is simulating that the switch will open up at t is equals to 0. So how will the resulting circuit look like? Well, if the switch is going to open up, look at how this will look like. It's like this part will not be there anymore. With the switch opened up, this is what you're going to have. But look at this. Even with the switch opened, do you see that the source will still be part of the circuit? So in this case, the resulting circuit is not source-free. So this one still has a source in the circuit. So you cannot argue that this is going to be source-free. In the same way, when you look at the one down here, what happens? Here, worse off, they're saying that initially the switch is opened. So again, pay attention to the action of the switch. Initially, the switch is opened. But at t is equals to 0, this is simulating that the switch will be closed. So since at t is equals to 0, the switch will be closed. Now, what do we see? We see that now the source is going to be part of the circuit, because the circuit will now have this, and then the resistor, then the capacitor here, then the resistor there. And obviously, in this circuit, the switch will be part of the source will be part of everything. So in this case, at t is greater than 0, the switch is definitely part of the action. So this is how you identify something that ends up being just a source free and something that does not result in that case. The two are quite similar even in the treatment. The only difference is that for this one that doesn't result into a source free, it will have a part in the expression that will have the forced response. So you will see that later on. For the rest of this class, we're going to look at these first two examples for source free and how to handle them. In this problem, what are they saying? So it looks kind of weird, lots of writing, kind of throws off students, but let's see what they're saying. Here we have a 120 volt DC generator. So 120 volt DC generator. So 120 volt looks like that's this one here. So they're saying that this is used to energize a motor. So here they're saying that this is our motor. Now you just want to pay attention to what they keep saying here. Whose coil? So they're saying that the motor has a coil that has an inductance of 50 Henry. Now, the fact that they're saying it has an inductance, so I think it has an inductance 1 and a resistance. So in other words, they're saying that this motor here can actually be viewed as just an inductor with that inductance and a resistor with that resistance. And then a field discharge, so a field discharge resistor of 400 ohms, that's this, is connected parallel to the motor to avoid damage to the motor, as shown in the figure. The system is in steady state. Determine the current through the discharge resistor. So here they're just using a lot of application statements. Otherwise, this is right within our boundaries. So how do you work out a problem like this one? Well, the first step is we see with the motor there, it might kind of throw you off, but let's interpret what the motor is doing to our circuit based on what they're saying. They're saying the motor is basically an inductor connected with a resistor. So let's show that. Okay. So since they're saying that the motor is basically about its coil, it has an inductance of 50 henries and a resistance of 100 ohms. This follows that in place of our motor here, we can replace this with an inductor. So I can put an inductor here connected in series with a resistor. So let me connect those two in place of the motor. So here I'll say I have a resistor. After a resistor, I'll put an inductor. So the two are in series like that. So the question said the inductor has an inductance of 50 henries. So here I'll say L is equals to 50 henries. And then finally, the resistor that has 100 ohms. So here I'll put 100 ohms. So this is how the circuit now reduces. Now they want us to find the current that gets to flow. So where they're saying steady state, determine the current through the discharge resistor after the switch is stripped. So after the switch is stripped, they're just saying after the switch is opened there. So to determine the current that will flow through that resistor, let's label the current that gets to pass here after the switch is opened as IT. Or you can just say I, but basically for any time t. And here we can say that from the source, we have the current that will be coming from the source. We can label this as IS. And then of course, we know to say that we're going to have some amount of current that will take this route. And then for this one, we can just label it as the current that goes to the inductor. Now, how does it go? So if you recall, for an inductor, we have the concept of the natural response. When this switch is opened, we're going to get the natural response only. And for the natural response, how does it look like? For the natural response, we did derive this expression. The current that will pass through, that will come from an inductor in a source free will be equal to, so we saw the initial current or the current at t is equals to 0, then too much there, let me just say I0 e to the minus the time constant over, sorry, not time constant there, time constant will be in the denominator, t over the time constant in seconds. So this was the expression that gave us the natural response from an inductor in a source-free circuit. So if you recall, the natural response from a capacitor was in terms of voltage, while the natural response from an inductor was in terms of current. Basically the same expression for a capacitor, but you just have V, it was V0, e to the minus t over tau. The difference was that for a capacitor, we had the time constant being equal to the resistance multiplying the capacitance. For an inductor, which is what we're looking at, the time constant will be equal to the inductance over the resistance in the circuit, in the source-free circuit. You'll see how. Again, here, we're just focusing on our inductor here. So we see that to get the expression for the current I coming from the inductor, we need two things. Firstly, we need to know what the initial current was, the initial current in the inductor. What was it? So this amount of current here, it's the current that was passing in the line with the inductor at t less than 0. So how much current was passing in that line? So at t is less than 0, how was the circuit like? So get the circuit, and they're saying it was tripped, meaning the switch was opened at t is equals to 0. Before that, the switch was closed. So if we simulate that behavior, at t less than 0, the switch was closed. We had this. Now, in this case, if the switch was closed for a long period of time, it now means that the inductor was fully charged. And if you recall, when the inductor is fully charged, it tends to behave as a short circuit. So when it is fully charged, it gets shorted out. Now, our I0 will be the current that will be passing through the branch with where the inductor was. That will be our I0 there. So we now just need to figure out how much current passed through this line, this branch here. That becomes our I0. So the way the circuit is, we see that we can easily use current division to figure out what I0 is, since the 100 ohm is in parallel with the 400 ohms there. So by current division, I0 will be equal to the other resistor over the sum of the resistors in parallel, then multiplying the voltage. Sorry, I'm using current division here. Sorry, I'm not supposed to use current division because it's a voltage that is supposed to be shared. So instead, I'll first get the current they'll have to share. Since these are in parallel, total resistance is going to be 100 by 400 over 100 plus 400. So I see that this is going to be 4 with 4 zeros over 500. So that now the 2 zeros will go with the 2 zeros. 5 into 40, that will go 8 times. So this will give us 80 ohms as the total resistance. With the total resistance figured out, I can now get the current that was coming. I've just combined these into one resistor. I can now get the current that was coming from the 120 volt supply. The current that will be coming from the source in this orientation will be the voltage divided by the resistance, which is 80. You see that the 0 falls off, the current from the source. So here we're getting 1.5 amps. Okay, now we know how much current is going to be coming from the 120 volt supply. Oh yeah, I think that was a quicker way of actually getting it without going through this. Yeah, I hope you guys were able to see that. But I'll still describe it. So since it's 1.5 amps coming from the source, we can now use current division. The current that gets to pass through, that goes to show up as I0, will be equal to the other resistor, 400, divided by the sum, multiplying the current they're sharing, 1.5 amps. In this case, so this is giving us 1.2 amps. So we see that in this case, the current that gets to pass through I0 there is going to be 1.2. Now, I did point out to say that other than going through first to find the total resistance, then use the total resistance to get the current coming from the source, there was a quicker way that you could have used to get the current that goes out as I0. I hope you guys saw it. Let me just describe it. It might be useful. So to get that 1.2, you could have also just seen that the way the circuit is, the 100 ohms and the 400, they are connected in parallel. If resistors are in parallel, they will see the same voltage, meaning that the voltage drop across the 100 ohms will be not 400, it will be 120. The voltage drop across the 400 ohms here, it will also be 120. So since I know that the voltage drop across the 100 will be 120, and I know that the resistance there is 100, I could have just used the 2 and Ohm's law to get I0 as the voltage drop across the 100 over the resistance there. Notice that this would have been 120 over 100, and dividing here, this would have still given us 1.2 amps. So this is why I was saying that there was a quicker way, and this was just to observe that since the two resistors are connected in parallel, they will both see, or they'll both have a voltage drop of 120 volts. This, as you can see, is faster to get the current through that 100 ohm resistor, which is going to come out as our I0. Okay, so with that described, remember our target is to get the expression for the natural response. We have just figured out what I0 is. Now we need to get the time constant. For an inductor, we did describe it. The time constant for an inductor, how do we get it? Well, to get the time constant, first thing that you do is, you see, you're trying to get this for when the switch was opened. So let's get our circuit and let's see what happens when the switch is opened. Okay, so there we have it. See, when the switch is opened, this gets to be open like this. If the switch is opened, notice that now the power source is not doing anything. So this line can all come out. This can come out. This is what we remain with. Now for this circuit that we now have, this has reduced to a source-free circuit. It's for this circuit that you want to find the time constant. And how do you get the time constant? We did see that for an inductor, it's L, the inductance, over the resistance. But you have to see or understand that the resistance that you put here, it's the total resistance in the circuit that remains. Here we count two resistors, the 100 ohms here and the 400 ohms here. The two resistors are in series, so you can just add them and say the total resistance or the combined resistance there will be 500. The inductance is 50 henries, so we'll have 50 there. The combined resistance for the two in series will be 500. If they were in parallel, of course, we know how we combine parallel resistors. That is how we would have proceeded. But in this case, they're in series, so we use this. This will go once, the 0 has gone there. 5 here, we're going to have 1 over 10. So this becomes our time constant, and remember, the time constant has units of the seconds. So now we can finalize our expression for the natural response. The current response that gets, this current response coming from the inductor, in the end, this is what will come out as our IT. So this current response will be equals to I0 e to the minus t over tau. So we already found our I0, 1.2, e to the minus, the time constant, t there is a variable over the time constant, t over 1 over 10. In the end, this is 1.2 e to the minus 10 t. And then the units here, this is current, but this will have the unit of the amp. For our second example, we have this problem here, and this looks interesting. They're saying assuming that the switch in the figure has been in position A for a long period of time and is moved to position B at t is equals to 0. Then at t is equals to 1 second, the switch moves from B to C. Find VC, find the voltage C at t greater than 0 for t greater or equals to 0. Okay, so how do we interpret this? The first thing is to understand exactly what the question is saying. Initially, the switch was in position A and it was there for a very long period of time. So we have something like this. What is this telling us? In this orientation, the passive device there, which is our capacitor, was charging. Since it was in that position for a very long period of time, the capacitor was charged to capacity, so it was fully charged. Then, after it was fully charged, at t is equals to 0, the switch was moved to position B. So the switch was then moved to position B, and this is what we had. In position B, what happened? This was from t is equals to 0. But it was only in position B for a second, because the question goes on to say that at t is equals to 1 second, the switch again was flipped, but this time it was taken to position C. Now this is the circuit that we had. And then they want us to find the overall voltage VC, a function of t. So how do we approach this? Well, just like the previous example, the first step, you know, to say this is a capacitor, the natural response there is in terms of voltage. Vt, which is what we are looking for as Vc, will be equal to the initial voltage at t is equals to 0, or before the switch was flipped, at the power minus t over tau. So just like before, we first want to understand what the initial voltage across that capacitor was before the switch started playing around. So how do we get that? Let's start with looking at what was happening when the switch was at position A. Okay, according to the problem, they're saying the switch has been closed for a long period of time. So let's look at what happens in that scenario. So while the switch was closed, we're looking for t less than 0, when the switch was still closed. What happened? You see, in this case, that is not necessary anymore. This resistor here is doing nothing to our circuit because it's not complete. This resistor as well doing nothing, not complete. Our circuit now just looked like this. But again, if it was closed for a long period of time, it now implies what here? So this implies that the capacitor here was, sorry, what do I have here? I think, this is, okay, so I think we're good. I just wanted to make sure that this was not a current source, but a voltage source, which it is a voltage source. I need to make sure that was the correct one I was working with. Okay, so when you look at what we end up with after doing that, we have this circuit that looks like this. So the two lines that we had there are not there anymore. But if the switch has been closed for a long period of time, it means that the capacitor has been charged to capacity. It is fully charged. And if you recall from our previous discussion, we did say that when a capacitor is fully charged, it tends to behave like an open circuit. If it is an inductor, when fully charged, it behaves like a short circuit. A capacitor behaves like an open circuit. So now, with the capacitor opened up, we want to find the voltage across these two terminals in the absence of the capacitor. Whatever that voltage will be, that becomes the initial voltage that the capacitor actually stored. But what will be this voltage? Well, with the capacitor behaving as an open circuit, there will be nothing happening to this resistor because current will come like this, and then finds this junction nowhere to go, so the circuit is not complete. So if this was a bulb, it will be off. So because of that, the potential difference that will be measured between these two terminals will actually be equal to what this source is supplying. Based on this, our V0 will actually just be equal to the supplied voltage of 12 volts. Again, it would have been different if this voltage was active. The voltage being measured here would have been less than 12 volts. But because this voltage source is not, this resistor is offline with the circuit incomplete, it now implies that the voltage V0 will still be the same as what was being supplied there. So V0 has been determined very quickly. With V0 out of the way, we now see that we are almost there, because the voltage response, VCT, is just V0, then e to the minus t over tau. So the only thing that is left here is the time constant here. So how do we get the time constant? We now want to analyze the circuit for t equals to 0. What did we do at t equals to 0? The switch was moved to position, our position was that, to position B. So what happened when the switch went to position B? Let's draw a circuit this time and see what happens there. So at t is equals to 0, the switch was moved to position B. So let's remove this, and then instead we'll just place our switch directly to point B. So this is how our circuit was. Well, nothing now connects to point A, so this is not doing anything anymore. The source is no longer active. This is not there. Let me just leave the resistor there. This is out. This is out. And then we only have the 500 ohms there. Again, C here is not doing anything, so you might as well remove it. So for time equals to 1, just at t is equals to 0, the switch moves to position B. This is how our circuit is going to look like. Well, what does it mean? What will be our voltage VC during this period? Notice that this will apply for t as t changes from 0 to 1 second before the switch again was changed. The orientation of the switch was changed. So in this case, our V0, since we are starting from 0, will still be what we found earlier, that 12 volts. But now we're saying in this orientation, for t equals to, as we start from 0 to 1 second, now the expression for Vt will be equal to the starting voltage, which is 12 volts, e to the minus t over, but what will be our tau? In this case, notice that the resistance, total resistance in our circuit, we only have one, which is that 500. Being a capacitor, it's RC. That is how we get our tau. Resistance is 500 ohms. Capacitance, 2 millifarads. So we're going to have 2 by 10 to the power minus 3 farads. And when we calculate this, we're going to get 1. And since the units for time constant, it's the second. So this will be over 1. Based on this, our final solution for this orientation will be e to the minus t. So that is what we are going to get there for t less than 1, from 0 only up to 1. That is what we're going to get. So you have to understand that this expression, this is what will govern the voltage response for time in the range from 0 to 1 second. Because from 0 to 1 second, the switch is connected to point B. So the response will be governed by this behavior. But as we now look at time greater than 1, because at 1 second, now they're saying the switch changes position. It moves from B and it is moved to C. What changes? Now, instead of connecting it to B, we'll connect the switch to point C. So now this is not doing anything out. Even the line with B there not doing anything, also out. Our circuit will now remain like this. In this case, what happens? We can get the voltage at C here for t greater than 1. This voltage will be equal to, again, it's the initial voltage which was present when this switch was closed, positioned to point C. And notice that here in this case, for point C, orientation C, the starting voltage which was present is the voltage at 1 second. The voltage which is a result from here. That is the voltage that we are going to start with in this orientation. So that is one key thing you have to understand. So that is the voltage you're going to start with. Other than that, everything else is pretty much the same. We have the exponent there. And then from the exponent, of course, you know to say this is going to be supposed to be e to the minus t over tau. But what do we have? We've seen that this must be the initial voltage which was present, not V0, the one we started with, but the V0 to this orientation. The 12 volts we had was the V0 to the first when the switch was moved to B. But when the switch was moved to C, the voltage which was present is going to be governed or regulated by that expression. Let's get the time constant for point C when the switch is at C. In this case, it's still RC, but the resistance here is different. The resistance for this orientation is 1 kilo ohms. So this is going to be 1000 ohms. Multiplying the capacitance, which is Q2, by 10 to the minus 3. Here, we just get 2 seconds as our time constant. Now, you have to understand one more thing here. You see, when we're evaluating it for when the switch is at C, our time is not really starting from 0. We are starting a second later. What does that mean? It actually now changes slightly. Since we are starting a second later, the time that we'll see here, it will be the actual time, but slightly behind or less by 1. If the overall time was, let's say, 5 seconds, the time we're going to see here will be 4 seconds. Why? Because the first second was wasted in the first orientation at B. So the actual expression now will be Vc, which is the one they're looking for any t greater than 1. This will be equal to V1, the result we had here, which is 12e to the minus t. So that will be 12e to the minus t, multiplying this part now, e to the minus time. We just from discussing that time will be less by 1, but over the time constant. And you've seen that the time constant will be a 2. So this becomes the expression that we're going to work with. So from here now, it's just a matter of simplifying this. We're saying E and E, when you're multiplying the same base, just add the powers. So let's see how we're going to add those powers. Okay, so let's see how the powers are going to add there. So in the end, we have 12. E, it will be minus T minus T plus 1 over 2. Basically, this is what the power is going to be. But now it's just a matter of simplifying it so that we combine this into one full thing. So single fraction, it's going to be minus 2t minus t. This will be minus 1 as well. Is it? Over 2. The negative here is for everything, so it will be, look at what I did there. I wrote a plus here. This is a minus, t minus 1. Okay, t minus 1 there. So the minus now distributes, it will make the t here a negative, to make the 1 there a positive. Yes. Single fraction, 2 multiplies, you have minus 2t minus t plus 1. And then this will be minus 3t plus 1 over 2. All in all, however you work it out, this is what you have. You can simplify it in so many different ways. Let's see how it goes. Okay, so yeah, just slight thing here. Notice that here I did take t here to be general, but you have to see that here when I'm substituting v1 here, this is for 1 second. It's how much voltage was present for 1 second. When we found it in the first place here, this was general for any value of time t. But we now want to use it only when t is equals to 1 second, because it will tell us how much voltage the capacitor was still producing when it was being connected to C. So when we are substituting it here, we're not necessarily going to put the general one with a t variable here. Instead, we're going to say this is for t is equal to 1 second, so that the voltage we get here will be the exact voltage the capacitor was responding with for t equals to 1 second. So the correct approach, the actual thing now, let's make a slight adjustment there. So this will now be equals to 12 e to the minus 1, since that will be t will be 1, multiplying. Now the t which is the other side, this is the general one. This is not a 1 like before, because this now will account for time after the first second. So this will remain e to the minus t minus 1 over 2. From here we can now combine to 12 e. So add the powers. This will basically just be, let's say, minus 1, then minus t minus 1 over 2. Okay, so this is better. This is how we're going to approach it. You can simplify it from here, or you can still evaluate this, since this will obviously give you an exact number. Or the way it is here, you can then try to write this as a single fraction. But basically, this is what is going to give you the voltage that they are actually looking for.